Thank you very much. Yeah, hi, my name is Marcel, and this is joint work with my colleague Miroslav Stankovic and my supervisors Ezio Patocci and Laura Kovac from Vienna. So yeah, this is the moment for probabilistic loops. So I'm going to present today a method to take a probabilistic loop and compute its moments exactly. So that's how the title is meant. So let's jump right into an example. All right, so here we have a probabilistic loop. And within the loop body, you see these probabilistic choices, probabilistic statements. It's only a snippet. The code goes on much longer. It's not that important that you understand it in detail. What this represents is a stochastic process with two players involved, and they have to fight or share a common resource. Right? And depending on the probabilistic choice, they either share this resource or they fight for it and have a penalty if they lose the fight. And when we want to analyze such a process, we can simulate it, right? So we fix a number of iterations and we simulate this program. And we take a few samples and we look at it and it's like, okay, what is happening to this balance of player one? That's the question. What is really happening here? Is it going up? It looks a bit like it's going up. If so, what is the variance? And what if we cannot sample this loop? Also keep in mind that we have to cut off at a specific point. So at a specific iteration, we can only unroll the loop so many times, right? So what happens after this cutoff point if we are sure that it increases up to this point? Wouldn't it be nice if we have like a method to compute literally the expected value in its closed form for the whole process up to possibly infinitely many loop iterations, and again, its variance. And this is exactly what our work can produce for such a probabilistic loop. It gives you the closed form for the moment, for the expected value, the variance, the skewness, and higher moments. And even we had this shared resource was a fixed number, and also the penalty. We can also compute it for symbolic resources, for symbolic penalties, also just for symbolic variables in general. And you can compute these expressions for the moments. Another example, take this probabilistic loop here, and you could imagine that it is embedded in a bigger program or in a bigger probabilistic model. And when you want to reason about this whole probabilistic model, because it contains a loop, you need some form of loop invariance. And the question is always, if you have a probabilistic loop, what is actually an invariant for this loop? And here you can have, for instance, invariance over the expected values or even higher moments. And here, these two equations here are two properties that are invariant for this loop. And the invariants are over the expected values of the program variables x, y, and v. And even more, these two are actually, so to speak, the only two polynomial invariants of this loop. So you can construct all other polynomial invariants from this loop. And also such invariants you can compute with the procedure I'm going to show you. So this is also the last motivating example. It's quite a fun example. So you have a loop, and we have this flag stop. In every loop iteration, we flip a coin whether to stop. So it models kind of a geometric distribution. And we also have these two additional program variables, x, which is always multiplied by 2, and we have this counter which keeps track of how many loop iterations will you take. And now, who of you is working with probabilities on a daily basis? Great. Then let's do a little bit of a quiz. Do you want to guess what is the expected value of the variable stop after termination? Anyone want to take a guess? 1, right? So because we terminate, right? So it is 1, and also the variance of stop will be 0 because there is no ambiguity after it. What is the expected value of the runtime? Not you. Because you know it, I'm sure.
2.
It's 2, exactly. So there we have some probability involved because also the variance is 2. And now maybe a tricky question, what is the expected value of x?
Doesn't exist. Doesn't converge.
Yeah, right. It's infinite. Yeah, it's a bit counterintuitive. If you can do the math, it's the correct answer. And yeah, good luck with finding this answer with sampling. Right. So you need some kind of formal methods to arrive at this, or some symbolic execution, or some more involved techniques. So with our technique, you can do all of these compute invariants, moments after termination, and all other things, also tail probabilities. You can bound the tail probabilities, but at the core of the technique is that we compute moments for the probabilistic loop. So the question is, how do we get from the probabilistic loop on the left side to expressions for the moments of the program variables parameterized by the loop counter? So for example, here we have the expected value of y, parameterized by how many loop iterations we had, and then we have like this closed form expression. And using these expressions also for instance, for higher moments, using such kind of expressions, we can do all these kinds of stuff that I showed you. The moments themselves give you already information about the process or about the loop. You can use it to compute invariants. You can use it to compute tail probability bounds. You can even recover or approximate distribution of program variables without sampling the loop. But the core is like, how do we get these expressions? How do we get these? And can we guarantee some form of computability, that we can always compute these expressions for some class of loops? And what conditions do we need for that? All right, so let's start slowly. Let's draw some inspiration from deterministic loops. A very simple loop here, two variables, x and y. And now the idea is that we use recurrence equations to model the values of these program variables. So recurrence equations describe a sequence of numbers, just like the Fibonacci numbers. There are 0, 1, 1, 2, 3, 5, and so on. And you all know that the Fibonacci numbers have these very famous recurrence equations that say the next term in the sequence is given by the addition of the previous two terms. The recurrence equations are a quite natural way to model program variables, arithmetic program variables in loops, because the value of a program variable in the next iteration of x or y in this example is completely determined by the values of the program variables in the current iteration. And so we can write down recurrence equations for the program variables that describe the values of the program variables as the loop is executed. In this simple example, just by inspecting the loop body. So x is initialized to 0, and x in the next iteration is x in the current iteration plus 1. We can do the same thing for the program variable y. And now what we can do is we can compute these closed forms for these recurrence equations. So in this case, we get that, for example, that the variable x has the closed form n. So we don't need to compute the previous terms in the sequence to get like the nth term of the variable x. And importantly, these closed forms can always be computed for this special class of recurrences. These are linear recurrences with constant coefficients. And for these kind of recurrences, these closed forms always exist and can always be algorithmically computed. So you might think, okay, they are linear recurrences, but despite the name, they can also be used to model nonlinear behavior. So if we have, for example, here, this assignment y is equal to y plus, or is assigned to y plus x squared, what you can do is you can start constructing the recurrences. For x, it's the same as previously, because the assignment didn't change. We can write down the recurrence equation for y. So in this case, y in the next iteration is y in the current iteration plus x squared in the next iteration, because the assignment of y appears after assignment of x. And now we have this recurrence equation, but there's this x squared there. But you can just consider x squared as a whole another variable and construct a recurrence equation for x squared itself. Right? You can, because here it's deterministic loop, the recurrence equation for x squared is literally just the recurrence equation for x squared. For probabilistic loop, this won't be the case, but now we have, again, a linear system of recurrences. If you're confused by the x squared, just replace it by your favorite letter, and then you have a linear system of recurrences, and we can compute the closed forms. And as a side note, this works, this modeling of nonlinear behavior works if the nonlinear dependencies are acyclic. We can use then these closed forms to do all kind of downstream tasks like computing invariants, for example. All right, but what can we do now about probabilistic loops? So for probabilistic loops, we cannot model the values of program variables by recurrences because, yes, the variables are probabilistic. But what we can do is we can model the moments of these program variables with recurrences. So for instance, the expected value of program variable v, in this case here, for this loop is just 1 because we draw from a normal distribution in every iteration, every loop iteration. The more interesting case is now, can we construct a recurrence for the expected value of x? And what you do is, you just, again, look at the assignment very similar to the deterministic case, and you apply the expected value operator on the assignment of x. So you get that the expected value of x in the next iteration is 7/10 times the left branch of this probabilistic choice, plus the expected value, like 3 times the expected value, 3/10 times the expected value of the right branch of this probabilistic choice. And if you do the simplification, you exactly get this expression here, which is a recurrence for the expected value of x. And you can do the same thing for the program variable y. And then because, again, like in the deterministic case, we have an x squared here, we need to, again, construct the recurrence also for the expected value of x squared, or let's say the second moment of x. And then, again, we have a linear system of recurrences. We can solve it, and we're happy. We can use them for all kinds of tasks, invariant generation, and other things. Yeah, but this was a very simple loop, right? It was, Benjamin disagrees. He thinks it's already impressive, but then let me impress you more. So what about this loop here? Right, this also in the loop at the beginning, we had if statements in this stochastic game that we modeled. So what about this loop here? Can this be done? We have here if statements, we have continuous distributions, we have symbolic parameters, like at the beginning you see S0, it's initialized to a symbolic constant. Yeah, probabilistic choice, polynomial arithmetic. Can this be done? Yes. So these are the closed forms. I was too lazy to type them into PowerPoint, so this is a screenshot from the paper. But how can this be done? So how does this work? So let me walk you through the steps, how we do this. So the first step is we compute the loop into a normal form. So we normalize the program. So here, for illustration purposes, I took a small part of the program we have seen before on the slide before, and we convert this program here into this program. So what happened here? So going from a loop to its normal form, we flatten the structure of the loop body. So we convert all the if statements and possibly nested if statements into guarded assignments. So previously you've seen here, we have this, for instance, if toggle is 0, then we assign x to this probabilistic choice. And here we have an x1 here. Don't worry about that yet, but we have this guarded assignment. So we convert if statements into guarded assignments. If you have nested loops, it's going to be a bit more complicated than this, but it can be done. Simultaneous assignment are expanded. Nothing special for that. But we also make sure that every variable in the loop body has only a single assignment. So using variable renaming, you just have to be a bit careful there, but it's also no magic there. And also all distributions have constant parameters. So for this, we use, for instance, like distribution properties that you can pull out the mean of a Laplace distribution, for instance. And then we get this loop here on the right side. Yeah. So you might say, okay, there were if statements before. Now we have guarded assignments. Did we do anything or just push the problem around? That's a very fair point because the guards need some more special care. And what we do is, first, we convert a guarded assignment into an unguarded assignment using Iverson brackets. Thank you for introducing Iverson brackets. So we push it into basically an equivalent unguarded assignment using these Iverson brackets. And now again, didn't we just push the problem around? Yes, but now comes the important part. Now we convert the Iverson brackets into polynomials. So note that in this example, the variable toggle was a binary variable. So it was only 0 or 1. And for this specific case here, the Iverson bracket is toggle equal to 0. It's just equivalent to the expression 1 minus toggle. And also is toggle equal to 1 would just be equivalent to actually the variable toggle. And this step is always possible for any guard if all the variables in guard have a finite type or have the same finite support over all loop iterations. So if you have more values than just 0 or 1, you will get a more complicated polynomial, but you can construct such a polynomial. And now this normalized program looks a whole lot like the very simple program we had at the beginning, like with the drawing from the normal distribution. And that's basically the idea. Now you can use kind of the same algorithm, or the same, I didn't show you an algorithm yet, but the same idea to construct the recurrences for the program for the moments of the program variables. As just one side note, if you watched very closely, I said that when you have nonlinear arithmetic in the loop body, the nonlinear dependencies have to be acyclic. And now you can see here in the assignment of x1 or of x depends on x1. And x1 depends again on x, but non-linearly because there's x times toggle. We have these program variables. So there is one additional thing you have to use. We have to ensure termination or a finite system of recurrences, we have to reduce these finite valued variables. For instance, I said toggle is binary. So if you take toggle to any power, it's just equivalent to toggle itself. You can scrap the power. Because 0 to any power is 0, 1 to any power is 0. You can do the same for if you have more possible values, but they have to be finitely many values. You cannot just then scrape the power, but you can replace it by a polynomial using only lower powers. For details, I refer you to the paper. But what you do now is, let me walk you very quickly through an example. If we want to compute the expected value, for instance, of the program variable L, we start with the assignment of L. It's right on the bottom, this x plus temp. So we substitute basically assignment of L into the expression expected value of L, and we get the expression on the right-hand side by also using linearity of the expectation. Then we just move up the loop body, and we substitute always assignments into this expression. So we get to the assignment of the variable temp. We substitute it on the expression on the top, and we evaluate the expected value on the Laplace distribution to get 0. We move up again, substitute the assignment for x, use linearity of expectation, and we move up like this. Now it's a little bit more involved because of the assignment of x1, but there is nothing fancy to it. It's just we use the definition of the expected value on this probabilistic choice. So you get this weighted sum of the two branches. And if you do some simplification, just algebraic simplification, you will get to this expression. And finally, we substitute the assignment for toggle to get to this expression. And if you simplify it, you arrive at the bold expression at the bottom. So here is then the recurrence equation for the expected value of L. Expected value of L in the next iteration is equal to the expected value of x in the current iteration minus 3/2 times the expected value of toggle t in the current iteration. So the algorithm is roughly you start with the goal you want to compute, can also be a higher moment, and you substitute the assignments bottom up. You simplify both algebraically and using properties of the expected value operator. You reduce the powers of finite valued variables. So if on the bottom we would have here expected value of t squared, we would just scrap the square because t is binary. And then you repeat this process because we don't have yet a recurrence for the variable t. You complete this to a system of recurrences, and then you can solve it and you have your closed forms. for instance, for this example, if you do this whole process, you get a whole bunch of recurrences, which are all linear recurrences. You can solve them, and you get this expression here, all these expressions. There are also some works who use like template-based methods and constraint solving to find out what are the moments of program variables in probabilistic loops. You're going to have a really hard time finding a template to compute the expected value of the program variable L here. So this is kind of an advantage of our approach. Now, very similar to the first talk, we have like kind of a contract. So can this always be done? What does the programmer of a loop or what have to guarantee that we can always do this? And a good part of our paper is about establishing this computability theorem, and it says that if you give us a program, a while loop in our syntax, which can contain polynomial arithmetic, if statements, distributions with known moments, also symbolic constant, then all moments of all program variables are computable in closed form if these two conditions hold. So if all variables in if conditions have a finite type and all nonlinear dependencies are acyclic. So these conditions are also in some sense necessary, because if we drop the first condition, then this would render our program model Turing complete, and you can show that you could solve the halting problem. If we drop the second property, or the second condition, then you can show that now our program model contains processes, stochastic processes, that have no known analytical closed forms. So we implemented all of these techniques, computing the recurrences, in our tool Polar. It's publicly available on GitHub. There is also an artifact available if you want to reproduce the plots and the results from the paper. And what you can do is, now for Polar, you just give it a loop like this. You say what your goals are, you press enter, and it gives you this closed form, which you can then also use to do other things. Or okay, here it's already executed again. This was the loop with the infinite, where the expected value of x was infinite. You can give it a list of goals. If you look closely, you can also give it this parameter after loop, and it computes you the expected value and the variances of the program variables after loop termination. You can also use it to construct these plots that I showed you at the beginning, to compare the exact expected values and the expected moments with just sampling. And it can do a whole lot more. You can also use it to approximate distributions. And you see here a whole list of options you can give to Polar. But in essence, it is a probabilistic loop analyzer. And at its core, there is this functionality that I showed you, constructing these recurrences and computing these closed form solutions, right, which you can then use, and that's also implemented in Polar, to compute bounds on tail probabilities, compute exact distributions for finite valued program variables, or also, which I'm quite excited about, you can approximate any distribution of any variable for all possibly infinitely many loop iterations without sampling them, without sampling the loop. So to summarize, there's this tool Polar, check it out. It's publicly available. And I presented to you this new method to compute higher moments for probabilistic loops, for variables of probabilistic loops, support for polynomial arithmetic, if statements, distributions, continuous distributions. We have a computability theorem, and there are then applications of this central method for invariant synthesis, distribution recovery, and approximation, and also computing tail probabilities and much more. Thank you very much. Sorry that I had to rush a bit in the end.
Yeah, while Marcel's phone is mic is being stolen. Are there questions? Yes.
So I'm trying to figure out if you could extend this language to support conditioning observations and still retain.
Excellent question. Excellent question. And it's actually, we are working on that. You can actually do conditioning inside the loop, but then also the question is, what does it actually mean to have? Maybe it's related to your streaming. Yeah, we talk about this, but all of these exact inference programming languages like DICE, SPPL, they don't support loops, and also even approximate inference. They have problems with loops, especially if you have possibly infinitely runs that are infinitely long, like a geometric distribution. And so we are currently working on using the moments to approximate basically the loop and replace it by something loop-free. So we would do like a pre-analysis and kind of surgically remove the loop from the bigger program it's embedded in.
So this may be a follow-up to what you just mentioned, but if you have the moments of the distribution of each of the variables at some arbitrary number of iterations, you should be able to reconstruct the full distribution of that variable from the moments, right, under some niceness mathematical conditions. So is that, I was about to ask if you could do this kind of surgery, but is that how you're planning to do this kind of loop surgical removal?
Yes, we're planning to do this. Under some niceness condition, you can recover the distribution if you have all moments, all infinitely many moments.
Right.
Yeah, we cannot compute infinitely many moments so, because we have to like.
Sure.
And then you're back. Yeah, it's known in mathematics as the finite moment problem. You can solve this, for instance, if your variable has a finite support, then you can solve it entirely. Otherwise, currently we have to fall back to approximation methods. But we can do approximation without sampling. That's then the advantage of the approach. But it's all future work.
Very cool.
Go ahead.
Could you use, if you have finitely many moments, to maybe have that as a representation, as a symbolic representation of many distributions?
Yes, I would think so. I mean, there are a lot of distributions. If you have finitely many moments, there are many distributions who have exactly these moments. So you could do that. I'm not entirely sure why it would be useful immediately, but yes, yeah, it's kind of an approximation and like a over approximation of,
So can you handle nested loops, and how would you do that?
No, nested loops, not particularly. You can use transformation to convert the nested loop into a non-nested loop. Yeah, and because I said also we can compute the moments after termination. So we have a loop guard, we can handle a loop guard, but basically on the loop guard we have to have the same restriction than on the if statement. So they have to be over finite valid variables. So if you have a nested loop, I think you could do, you can convert it into a non-nested loop.
Some cases, yeah, sure.
In some cases.
Sure. Thanks.
Didn't Cozen prove that you can flatten to one loop, even for probabilistic?
In theory, yes.
Yeah, okay. Yeah, okay. Okay. I have a serious question, though. So are you familiar with this, how's it called, Skolem problem? Does that play into your framework at all, the difficulties with not knowing how to solve the Skolem problem? And if not, why not?
No, it does not play into our. We actually have in our group a very brilliant postdoc who works on the Skolem problem. So the Skolem problem is asking if you have a linear recurrence, does it have a zero? And it's one of the most famous problems where we don't know if it's decidable or undecidable. So having the Skolem problem would, for my programs, would be you have the closed form and you ask, does it have a zero? Which is solvable for my recurrences because they're all first order recurrences. There's a bit more to that, but I tell you offline, but it's not always solvable.
So it's not about finding the closed form, but deciding whether.
Then, yeah.
right. Yeah, are there more questions? No. Otherwise, thank you for sticking around to the probabilistic session. Let's thank Marcel again.